the invitation. It's an absolutely spectacular building, and I really look forward to visiting frequently in the future. I suspect, like a number of speakers at this meeting, our plans for what to talk about were significantly perturbed by the events of 13, 12, 11. So, of course, while many of us roughly knew what was going to happen, still, I have to say, to my mind, the story was even more convincing than what I had come to believe through the rumors. So I'm giving a rather different talk than the one that I was planning to give a week or two ago. It'll have some overlap with some of the things that Savas talked about. Some emphases will be a little different. I should also say that we've been waiting for the Higgs for a very, very long time. So this is not one of those situations of an incredibly surprising discovery with and then lots of creative thinking about what it might mean. Instead, I think it's an example of a discovery that we've been waiting for, and it's more a question of trying to sort out what the implications might be. So that's just a caveat to say there'll be no references throughout this talk. There'll be a lot of things that are common knowledge or have been pointed out by other people. I won't be saying who did what, when, where, and how. A testament to how expected this physics has been is the 97 papers that have appeared in the 3 days since the announcement. I don't know if that's the exact correct number, but it's order of magnitude correct. So instead, I'll be giving at least my own perspective on what this means. Towards the end, I will mention some work in progress with David Kaplan, and which is really based on work that he's been doing with his students Arpit Gupta and Tom Zarowski. Okay, so I think the most exciting thing that's going on is that we are finally in a data-rich era in fundamental physics. This hasn't happened for a long time. Now, I just want to spend 2 minutes saying a little bit about what I was going to say in my other talk, and then abandon it. There's one sense in which we're in a data-rich era completely obviously, which is experimental data, and that's significantly perturbed and is impacting how we're thinking about things. There is another sense in which it's a remarkable data-rich era, which goes back to some of the things David was talking about during his talk, and it's something which I think has been going on, which is really extraordinary in the subject, but is somewhat flying under the radar as far as the degree to which I think it's actually appreciated, what amazing things are going on. And this is associated with another kind of data richness that has been accumulated over the past 10, 20 years, but more and more of it's being mined and more of it's being understood. It's a kind of theoretical data about the structure of quantum field theory itself. And more investigations over the last, really, 2 decade, but more and more work is unearthing more and more remarkable, extraordinary structures that are hiding inside good old-fashioned quantum field theory, which, as David reminded us, is now the same as revolutionary string theory. So there's really something amazing in this way of putting quantum mechanics and space-time together that was handed down to us in the 20th century, but seems to have structures in it that, if we really understand them better, at least I strongly feel hold the promise to give us a new way of thinking about what space-time and quantum mechanics really are. So that's something which I think is going to be at the cutting edge of theoretical developments for this decade, for the next decades, however long it takes for a really major, obvious breakthrough to happen. There have been lots of more minor breakthroughs that have been happening all the time. But anyway, that was going to be half of my talk before, but I'm not going to talk about that at all, given the good fortune of the Higgs announcement coinciding with this meeting, and the rest of it will be dedicated to thinking about the implications of having discovered a Higgs at 125 GeV. And I should say that this is, now, my default is that we have seen a Higgs, its mass is 125 GeV. This could be wrong, but it's my default until proven otherwise. So I'm going to assume this is true until something convinces me that it's false. So, what's the first lesson? The first lesson, and very important lesson, in fact, the central lesson, of which all of our other problems descend, really, is the triumph of weak coupling. We are used to even telling our poor grad students that the Higgs mechanism is boring and simple, and all these more exotic things could be happening. It's weakly coupled, all these more interesting things could be happening. Whereas in fact, it's exactly the other way around. It is simple, it is weakly coupled, but it's actually astonishing that such a simple, weakly coupled theory describes the electroweak symmetry breaking in our vacuum. It's an absolutely astonishing, remarkable fact. Everywhere else in nature, in a state of nature, where we see large hierarchies generated, where we see this sort of symmetry breaking phenomenon, it is associated with more exotic, strong, interesting dynamics. Technicolor, here thought of as just a stand-in for strong dynamics for electroweak symmetry breaking, is a far more conservative idea for what might be going on at the weak scale, because that's what happens everywhere else in nature, everywhere else in condensed matter, everywhere else in other situations that we're familiar with, even in QCD. Okay? Everywhere else, that's what we've seen. So this is the first lesson. It's not strong dynamics. We have evidence for weakly coupled electroweak symmetry breaking with the simplest possible picture of a single scalar field. And the reason that's remarkable and kind of shocking is that the only other times we've seen such an effective theory, and we do see such effective theories elsewhere, we see such effective theories to describe physics in the neighborhood of phase transitions. Everywhere else that it happens, so here's a bunch of electrons in some material where the temperature has been tuned to put it close to a phase transition where all the electrons are lining up, the correlation length is long. Here's a little electron in this metal who sort of looks out and sees, as far as the eye can see, there's spins all pointing up in the same direction. There's this large correlation length, much larger than the interatomic spacing, and they wonder, why is this? This is amazing. Why is there such a macroscopic scale so large compared to the interatomic spacing? And such theories do exist. We engineer them all the time when grubby experimental grad students do their experimental labs in preparing to do real stuff. And it's always accomplished by someone sitting out there and fine-tuning, adjusting the dials of a knob, adjusting the temperature very accurately to put you close to the point of the phase transition. That's why it's so surprising. We have seen such theories before in nature, but the other times we've seen them, they've involved a significant fine-tuning to put the system close to a phase transition. So of course, that's why we expect, that's the problem of naturalness, that's the hierarchy problem, and it's why we expect that there should be some physics coming in near the TeV scale, not to have it be fine-tuning in this case. And that's what's so extraordinary about seeing this as a property of our vacuum. In a state of nature, with no obvious person outside twiddling the dials, we're seeing an effective theory that looks just like other ones in situations where there is someone twiddling the dials. So we assume that this is a doctrine, this is the ideology of naturalness, that will not happen in this case. There will be some new physics right above our head to solve the problem. This is the argument we all know for a long time. Something else we've known essentially from the get-go, essentially from the late 1970s and early 1980s, where these ideas first solidified, is that there is going to be a central tension. Because imagining that the standard model makes sense all by itself to very high energies, immediately has a benefit. It explains all the accidental symmetries that we see, baryon and lepton number, CP, flavor, and so on. So, and there are probes on the scales where these symmetries could be broken. Huge scales for baryon and lepton number violation. Scales of order hundreds to thousands of TeV for flavor and CP violation. So on the one hand, we would think there shouldn't be physics until such incredibly high energy scales in order to have a good, clean explanation for the absence of all these effects. On the other hand, naturalness tells us to put a ton of stuff right above our head at the TeV scale. So there's an obvious conflict between these two ideas, an obvious tension. And part of the attitude in physics beyond the standard model building for 30 years is that these aren't problems, they're opportunities. It's a perfectly reasonable and good attitude. Is that, well, what's going on? Yes, if we did something totally stupid and generic, we would have all these big problems, but there's some beautiful structure, there's some mechanisms, there's some dynamics, there's some ideas involved that are going to make it possible to put all this stuff above our head without having noticed it. Now, I'm not going to talk about other approaches other than supersymmetry. We could talk about them later, but I'm going to talk about supersymmetry because it's the best one. Supersymmetry around the year 1990 looked as spectacular as it has ever looked. There was an incredible unification of couplings that was given to us by LEP. together with the existing wonderful picture for a thermal relic dark matter that it provides. So this is an absolutely spectacular picture. As is also well known, things started getting logarithmically worse from there as a function of time. And there are a variety of ways that people talk about the fine-tuning problems. I completely agree with what Sava said. I'm sure what many people say, that intelligent people shouldn't fight about definitions of fine-tuning. But in fact, I want to phrase what this difficulty is with low-energy supersymmetry in a way that's less has to do with some numerical fine-tuning and more has to do with some sort of parametric picture that you would expect for what the spectrum would look like, which is just very unlike what we see the spectrum actually looks like. So in a supersymmetric picture of the world, very roughly speaking, you would expect that squarks are heavier than leptons. Colored things get heavier under the renormalization group compared to other guys. So there is a first kind of hierarchy. You might expect squarks heavier than leptons. But there's a coupling which is even bigger than the strong coupling constant. It's the top-Yukawa coupling. The top-Yukawa coupling mixes up the Higgses and the stops. And so what you'd really expect is that the Higgses and the stops are dragged together by the top-Yukawa coupling, which are in turn heavier than everyone else because the stops are colored. That's the sort of spectrum you'd expect. Drawn in a sort of standard picture that people draw for example, what happens to the evolution of the Higgs mass and the stop mass as you run from some high-scale lambda SUSY breaking, where supersymmetry first, SUSY breaking soft terms first appear in the effective Lagrangian. There's a sort of standard picture where the Higgs mass squared goes negative, maybe the stops don't, the stops keep going positive, and so on. And when I used to teach this 10 years ago in field theory courses, and as an example of the way the renormalization group works, I would tell students, please don't be confused about the scale where this crosses zero. The scale where this crosses zero has nothing to do with anything. It's completely random scale. It has to do with some funny ratios of dimensionless quantities that's set in the ultraviolet. You just have to keep running until you get down to the TeV scale or the soft mass scale, and that's to sum all the large logs, and that's what's going on. So this is what, if you had to guess, where you stop running, of course, is just set by the scale of the soft masses. If you had to guess, you'd expect the picture looks a little like this. And so the Higgs and the stop and everyone else, the Higgs and the stops are comparable and are heavier than the leptons and the electroweakinos. This is a sort of spectrum that you might think is natural. Of course, there's exceptions and so on and so forth. But this is a sort of spectrum that you might think is natural. This is the reason why very sober Italian theoretical physicists, who you can guess who they are, not me, not yahoos, very sober, serious people, really thought that SUSY would be discovered at lap 1. It wasn't some wild fantasy, it was this picture. Okay? Now, what is the picture today? It's sort of independent of anything. The picture today is more like this. It's that now we know the stops, other people are getting heavier, and the picture looks more like this. That you run, and you cross zero, and it just so happens the scale where you cross zero just happens to coincide with the soft mass, so you stop running right away within a sort of a third of an e-folding after you cross zero. So there's a complete coincidence between two scales that have nothing to do with each other. If you actually plot what it looks like, it really looks like that. Okay? And this is, of course, associated with the fact that instead of things looking like this, we have the Z, the W and the Z, now the Higgs, at the bottom of the spectrum, and we don't know where the top of the spectrum is. But there's this just qualitative difference between what it wants to look like, and what it does look like. If you like the difference between the natural spectrum and the nature-old spectrum, the actual, not what's handed to us by theorists, but what's handed to us by nature. There's an associated problem with this. It's not the same problem. It's a closely associated problem, but it's a milder problem. In the MSSM specifically, you see the problem I'm talking about, it doesn't even much have to do with the MSSM specifically. In the MSSM specifically, there's an associated problem that has to do with getting the Higgs heavy enough. To get the Higgs heavy enough, we have to have large supersymmetry breaking corrections to the Higgs quartic coupling, which in the MSSM comes from threshold effects and logarithmically enhanced effects from integrating out stops. This already, as you all remember, at 115 GeV was uncomfortable, somewhat uncomfortable for low energy supersymmetry, and another 10 GeV on top of 115 doesn't improve the situation, obviously. And as Savas mentioned, even in this sense, the tuning is a percent, third of a percent, whatever, something like that at best. Now, this is not a big deal. necessarily. There are, as Savas also mentioned, there are extremely simple extensions of the MSSM, perfectly fine in keeping with the ideas of naturalness, which can just hoof the Higgs mass. And I'm just summarizing the two mechanisms Savas said just in this little slide. In order to get a positive correction to the quartic coupling, we have to get them from F terms or D terms that don't decouple, so that we can't integrate out things supersymmetrically to get these things, otherwise the effects would decouple. So it has to be effects that are associated with supersymmetry breaking. We can have non-decoupling F terms, non-decoupling D terms. Standard examples are the NMSSM, which allows us to get this extra quartic coupling. And the rough formula to remember is that the Higgs mass in these theories is what it would be in the MSSM at biggest, plus a correction that lets you go higher. That's in this example. In this example, a non-decoupling D term, I can take the MSSM and just add a U1x, just a very simple U1, our favorite U1 that comes from SO10. The Higgses are charged under that U1x, and if it's broken through with big, if the U1 is broken through large soft masses, so we get a non-decoupling D term, and we increase the Higgs mass squared again now by something that goes like just have normalized the ratio of the G squared to the X to the coupling to the Z times mZ squared. Now, in both cases, let's imagine that from all the other usual effects, heavyish stops or whatever, we take this up to 115 GeV, the situation we imagined before. Okay? That's what we have to deal with the left bounds. Then, of course, in principle, we could make these corrections as big as we want. But there are some rough guidelines that we might like to have. For example, we might want to keep this beautiful supersymmetric picture of gauge coupling unification. So that puts upper bounds on how big these couplings can become. And so there's an upper bound to how big a boost you can get, limited by the UV in both cases. And it turns out if you roughly saturate that bound, you roughly go up to 125. Okay? So the take-home message is that natural supersymmetry today, with the extra dipsy doodles of non-decoupling F terms and D terms, is about as good as the MSSM was with the left bound. Okay? That's, I think, the way to think about it, which is not so bad. Which is just fine. It might very well be the way things are. There's absolutely nothing wrong with this. And I want to emphasize also a point that Savas made, I think extremely important point, so I will say it again, that if we measure a 20% deviation in any of these couplings, 20% deviation in those couplings could give us an order factor 2, 1.5 to 2 deviations in the rates compared to the standard model. Of course, this number at 1.5 to 2, we're not picking randomly. We're taking these very weak hints of some deviation from this data. We're just looking at that to get an idea of the sort of magnitude of effect we could be talking about. But let's say something as big as a factor 2 effect. Factor 2 effect that, let's say, raises everybody's production cross-section. Easiest way to do that is to reduce the coupling to BB bar by 30%. Okay, so that just reduces the width, the overall width by a factor of 2, raises all the other branching ratios up by a factor of 2. That's one simple example. But any indication for something like this is as dramatic a thing as we could possibly get. Even if we don't see any new particles, we don't see squarks and sleptones or gluinos next year, if there's any firm evidence for this, that's huge, because it means that we absolutely must have extra new light states that participate importantly in electroweak symmetry breaking. Okay? In fact, if you look at these couplings, these couplings, especially these big ones, are famously the couplings the Higgs is supposed to have to unitorize WW scattering, to make sure that all the scattering amplitudes are well behaved. If you're going to monkey with them at the 30% level and also not screw up this perturbative picture of electroweak symmetry breaking, you simply must have new light states lying around. And so this would be an enormous support for naturalness, absolutely enormous support for naturalness, even if we don't discover one new particle beyond the standard model. For example, if we take this example of a 2 Higgs doublet model, or this boost to the quartic coupling that we expect to get in the NMSSM, just integrate out the second Higgs doublet. A nice way of thinking about this is that there's a non-trivial functional dependence on the B quark on the Higgs web. And we can just look at the ratio of the Higgs to BB bar coupling here compared to the standard model. And it has a very, very pretty form. It's literally given as a ratio that measures the amount of the mass of this second Higgs doublet, which is coming from electroweak symmetry breaking. Nothing to do with tan beta, no details, literally just that nice ratio. And again, if we demand that these couplings don't get too big, so we have a nice ultraviolet story, in order for this effect to be big enough to boost the cross-sections by a factor of 2, we must have a second Higgs doublet right above our head at 230 GeV. Okay? So it's just an example of the fact that if there's deviations in these couplings, there's necessarily new light states associated with electroweak symmetry breaking in an important way. Ergo, unnaturalness is out the window. You know, if the theory is going to be unnatural, you're killing yourself to fine-tune one guy down. There's no reason on Earth to fine-tune more than one guy down. Okay? So anything like that is just immediate evidence that something natural is at work. So, for the rest of the discussion, I'm going to then assume that I'm not taking any of those hints seriously. I'm looking at the sort of broad lessons that at least I want to extract from what we've been learning over the last 20, 30 years, as things have been gradually getting pushed to more and more and more tuning. And I want to open up the question of whether the weak scale could be tuned. Now, when people talked about these possibilities many years ago, there was all sorts of philosophical arguments about the anthropic principle and things like that, and I want to fully avoid any discussion of that sort by just focusing on a simple physics point. Okay? Have we seen fine-tuning in other effective theories in our neighborhood? And the answer is absolutely yes, if you go down one effective theory down from us, from the weak scale down to the scale of nuclear physics. Nuclear physics is complicated or hard to learn, at least for people like me. I used to think it's because I was just too dumb to understand it, but it turns out it's not because I'm too dumb. It actually has two fine-tunings in it, which makes it hard to understand what's going on. So the two well-known tunings are that first, the deuteron binding energy is a lot smaller than you'd expect, again, just from the scales in the problem. This is around 2 MeV. All the rest of the scales in the problem are around 100 MeV. That's a 1 in 20 tuning. There's another tuning, which is actually a lot more dramatic. If you take two neutrons, they are not bound. They're not bound by around 60 keV. Now think about that. That's completely ridiculous. All the scales in the problem are 100 MeV, and yet they're not bound by 60 keV. That's about a part in 1,000 accident. Okay? Just looking at the next theory down. There are these two accidents. In fact, these accidents are officially fine-tunings in the effective theory for that governs few nucleon nuclear physics. There are two 4 Fermi operators in this effective theory. They're both fine-tuned to within part in 20 and part in 100 of certain ultraviolet fixed points. What do these tunings have to do this? They have to do, amongst other things, certainly with the up and down quark masses. If we vary the up and down quark masses, we would definitely vary these things. And so at least there's some indication that there is some kind of fine-tuning. Who knows where it comes from? But there's some kind of fine-tuning that certainly depends on electroweak parameters. And if I take this one and that one together, taken together, it's about a part in 10,000 fine-tuning, just in describing nuclear physics. Now, I'm not going to get into this reason to be wary of naturalness arguments, the famous problem with the cosmological constant, because I want to avoid the A word for as long as possible. Okay. So these were some of the motivations that led to take seriously a spectrum which many people had run into for years and years. So but what the idea was to take it seriously and not be ashamed of it. So the idea of split supersymmetry is to imagine that in the supersymmetric standard model, the fermions are light, but the scalars are heavy. Heavy, in the beginning, meant hundreds of a TeV way up. We even imagined they could go way, 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 way up. Immediately, this preserves unification, it preserves dark matter, and it just cancels out instantly the flavor, CP, and moduli problems. So that was the motivation. And the idea is, of course, it's fine-tuned. It's fine-tuned. It is very, very fine-tuned, but maybe something else is dealing with the fine-tuning problems, just as it is for the cosmological constant. Now, when you actually try to run this story to see is it possible to get a splitting between the scalars and the gauge nodes, of course, every model builder knows that it's possible. In fact, it's so possible it happened right away when people first started building theories of supersymmetry breaking in the MSSM. The first models of SUSY breaking exactly had this feature. The gauge nodes were light and the scalars were heavy, and it was thought of as a problem because it's very, very fine-tuned. Okay? This happens over and over again for the obvious reason that all you need to do to give the scalars a mass is break supersymmetry. To give the gauginos a mass, you also have to break R-symmetry. And breaking the R-symmetry takes more work. Okay? That just happens. The modern guise of this is in the context of hidden sector supersymmetry breaking models, which are completely generic. And if you just break supersymmetry in a hidden sector, you don't imagine any sort of fancy mechanisms in there. You don't imagine that it has singlets with higher dimension operators that give you directly gaugino masses. Just a garden variety hidden sector theory. There was a beautiful observation in the late 90s of the idea of anomaly mediation, that even with no direct couplings, there is an anomaly-mediated contribution to the gaugino masses, which is a loop factor down compared to the gravitino mass. Now, if you do nothing else, the scalars are where the gravitino mass is. Okay? So right there's a loop factor, let's call it 10 to 1,000, splitting between where the gauginos are and where the scalars are. Now, there are two groups who discovered anomaly mediation. The anomaly-mediated effect for gauginos, the CERN group and Randall and Sundrum. The CERN group didn't further notice a clever mechanism for suppressing the scalar masses. Okay? So this was the attitude. Actually, there was a clever mechanism for suppressing the scalar masses, the idea of sequestering. That clever mechanism had predicted that the lepton was tachyonic, for example. Okay? But that was thought to be infinitely preferable to having very, very heavy scalars. Okay? Thanks. Again, this was an example of not a problem, but an opportunity. But you have to do something special to make that happen. And if you just ask, you break supersymmetry in a hidden sector, what does the spectrum want to look like? This is the spectrum. This is what the spectrum wants to look like. Okay? 100 TeV scalars, TeV fermions. And if this is the picture, there's a tuning of order 10 to the minus 4 to 10 to the minus 6 for electroweak symmetry breaking. The 10 to the minus 4 end is not far from the little tunings that we saw in nuclear physics. So this is not some spectacular amount of tuning. It's a relatively modest amount of fine-tuning. But this is what theoretically the models want to do. It's what the models want to do, and model builders were fighting it because they wanted to preserve a natural picture. Okay? But I think it's reasonable to let the theory do what it wants to do and see where it leads you. So let's let them do this. First of all, I want to stress something, that if you want to make the scalars much heavier than the gauginos, or rather, if you want to imagine the gravitinos getting much, much heavier, let's say comparable to the scalars so the gauginos are light, then you have to find some way of shutting off the anomaly-mediated contribution. And there are ways of doing that, but that's yet another mechanism, another sort of structure that's got to be there. Without some extra structure, this sort of loop factor splitting is what really comes out naturally. Okay, so now let's go and see what this picture implies. First, we'll go back to the plot that Savas showed us. I'm essentially making the same point. If we just imagine that we have scalars between 10 and 1,000 TeV over a nice broad range of parameter space in this theory, the Higgs is naturally heavy enough. Okay? 125 GeV is not a problem. Here's another way of illustrating the same plot, by this wonderful paper by Jewish and Strumia that came out in August. Okay? So at 10 TeV, 100 TeV, and 1,000 TeV, you have more or less large tan beta, moderate tan beta, smaller tan beta closer to 1, in order, and yet be consistent with this purple line of what the 125 GeV Higgs wants. So that's a first interesting point. This value of 125 GeV is not 150. 150 would have been fine with incredibly heavy scalars. But 125 is right in the neighborhood of this moderate split spectrum with scalars between 10 to 1,000 TeV, which is also what supersymmetry breaking theories want to do. And again, I stress this is not the most radical story with scalars incredibly heavy. As Savas also mentioned, there is a possible smoking gun associated with this picture, which is that the gluino could be long-lived. In order to see a displaced vertex at the LHC, oh, sorry, that should be the, right. In order to see a displaced vertex at the LHC, the squarks have got to be heavier than, the going rate is around 500 TeV, and there's something here which is a mass difference between the top and the bottom of the spectrum over a TeV to the 5/4. So if there's a pretty split spectrum, unless the squarks are 500 TeV or heavier, we're unlikely to see a displaced vertex. Okay? But we may well do. All right, so that's what the theory wants to do. At least this class of theories wants to do. Now, the obvious worry. What is an obvious worry? Well, one of the motivations for having the bottom of the spectrum be where it is the WIMP miracle. That the WIMP miracle relic needs us to have light gauginos and Higgs-inos. That's still perfectly possible, but the obvious worry is that there's a very straightforward way. If we're going to have the philosophy that everything's going to run as straightforward as it wants to, the most straightforward way of having a WIMP would be to just have it annihilate through the standard model gauge interactions. And that means a Higgs-ino at 1 TeV, a WINO at 3 TeV. That's got to be the bottom of the spectrum, and so long any signals at the LHC. That's always been the worry with this picture. It's not necessary because the dark matter could be lighter and even be a relic. But again, if we're just going to just run things in the most straightforward possible way, that's always been the worry. 2 short comments about this. I'll just be 3 more minutes. 2 short comments about this. One is that, of course, we could have a relic only constitute part of the dark matter. This is actually reasonable from a number of points of view, which I don't want to go into now. The rest could be, say, axions, and then that could lower the spectrum. A second point is that, in fact, the relic might be irrelevant. That in these pictures, they're also moduli at orders hundreds of TeV. The moduli decay late. They're heavy enough that there's no moduli problem, screwing up Big Bang nucleosynthesis. But when they decay, they do wipe out the abundance, the relic abundance that you made, and in turn repopulate all the dark matter particles. So you might worry that that removes the connection between the dark matter and the TeV scale. But early studies of this done, in fact, my student Jared Kaplan's very first paper as a graduate student was working this out in precisely this context of this mini split scenario. And you find that there's actually a preference, continues to be even more of a preference of light dark matter. Okay, so this is another reason to expect that we might actually see something. Okay, so let's keep going now. So that means that it could be that the bottom of the spectrum is lighter. But let's return to the kind of nightmare-like scenario and just see what it looks like. So let's really imagine we want a thermal relic. Let's just see what it looks like. It's a totally vanilla story. Okay. So here are just the honest cases. Okay. We could have the Higgs-ino down here at 1 TeV, maybe the WINO up here somewhere above it, but then in completely standard anomaly mediation, we get these ratios of mass scales that will put the WINO down here, a huge jump up to the gluino, and then up to the scalar masses, and just forget it. Okay? Just absolutely forget seeing any of these particles at the LHC. Okay? So that's one possibility. It could be. It could even get worse. If the Higgs-ino isn't down here, the WINO is the LSB, then we have an even bigger jump. Right. But really, let's go back. That's quote-unquote standard anomaly mediation, but it's not really the simplest picture. Let's really continue to take the philosophy of letting it do what it wants to do. For example, we don't have to play any gymnastics anymore to suppress the mu term. In fact, in all of these theories, there's a completely natural way of getting the mu term via the Giudice-Maziro mechanism. Now, here's where things get interesting. Anomaly mediation is very ultraviolet insensitive, except when there are particles that get a very, very big source of SUSY breaking. And precisely these scenarios where we have the masses and B terms for the Higgs-inos coming from Giudice-Maziro is an example of a completely non-decoupling effect. Okay? So when you, sorry, it does not keep you, it destroys the ultraviolet insensitivity of anomaly mediation. If I say it another way, if we have a whole bunch of very non-supersymmetric spectrum of particles up at a few hundred TeV, there are large threshold corrections to the low energy anomaly mediated results. And so this is what happens if you really let it go. You let the Higgs-inos go up to M3 halves. Everything is up here. And what you notice, it's still not so hot for the LHC if the bottom of the spectrum is at 3 TeV, but the splitting now is a factor of 3 rather than a factor of 9. Okay, so the non-decoupling effect has the opposite sign. It's calculable and has the opposite sign. And that's what inspires you to imagine that there might be other things up there at a few hundred TeV. Let's just imagine that we have some vector-like matter, 5 + 5 bars, and that they also get their mass, just like the Higgs-inos, through the Giudice-Maziro term. And all of a sudden, life gets a lot better. So the splittings between the bottom and the top of the spectrum are just for numerical reasons, having to do with the values of the beta functions and things like that, are always squashed. This is the case with one messenger this case with 3 messengers, the bottom and the top, there's a factor of 2. Remarkably, with 2 messengers, it turns out that all the gay genomes are on top of each other at leading approximation. Okay? Yes, I am. Yes, sorry, yes. And so, just say, in all of these cases, you find that the ratio of the top to the bottom of the spectrum is less than around 2.5. That means that even if you put the bottom of the spectrum in the worst possible place as far as thermal relic dark matter is concerned, in all of these pictures, there's excellent prospects for LHC discovery. And there was this wonderful happy accident in the case where they're all on top of each other, which just happens for completely, these are just formulas involving, beta function coefficients, but some accident happens between these numbers that to leading order makes all these guys degenerate. There's a splitting between the gluino and the wino that comes from the heavy squark thresholds. That means that the splitting there can be between 50 and 100 GeV. And in this picture, you naturally get displaced vertices, even if the scale is at around 100 TeV, because what controls the width is the delta M and not the mass itself. So you might imagine 3 TeV gluinos, but with millimeter to meter displacements, just completely naturally from this picture. And of course, I'm emphasizing this is the sort of worst, this is letting everything go as vanilla as possible and see what happens. If you do that, there are cases that are bad, and there are cases that are very good. We don't know what nature is going to give us, but it is worth keeping in mind that there really are, even in this extreme picture, there are very good reasons for optimism at the LHC. Okay, let me conclude. So the Higgs at 125 GeV. Of course, you can say it looks like the standard model, but to my mind, it really looks supersymmetric. It's within spitting distance of what you'd expect supersymmetrically, just a zeroth order statement. Now we're talking about things that are very important, but still first order details. And it's an absolutely fantastic, wonderful, intermediate, confusing value, because it does not force us to make a choice here, but it makes the choice more stark between a pretty natural explanation and just letting the scalars go and swallowing a tuning of order a part in 10,000 to a part in a million. And to my mind, at least the way I've told you the narrative, the tides of history plus the new data just continue to push us in this direction, which makes it, I think, at least compelling to think that we might see a version of fine-tuned supersymmetry. But I repeat again that a single piece of data in the next year would demolish this picture instantly. If there's any indication, any deviation in the sigma times branching ratio for Higgs production and decay compared to the standard model, dead. Okay? It's not this picture immediately. So just to conclude, this is an absolutely deliriously exciting time in fundamental physics, and we all wait on pins and needles for the ATV run in 2012, and hopefully we will have another meeting here in not too long to discuss the implications when we know more. Thank you very much.
Thank you, Doctor. We have time for few questions, if any. Please raise your hands if you really need it. One there, yes.
Why were you so pessimistic?
Huh?
Why were you so pessimistic?
Why was I so pessimistic?
I'm joking.
Oh, sorry.
Well,
No, I was pessimistic. I was more pessimistic about this picture. And
don't worry, we understood.
Yeah, okay, it was a joke. All right, well.
Well,
Well, then you're missing a spectacular opportunity to learn why I'm so pessimistic.
So, any other hand? If not, we thank you very much again.